the recording one. Now it's fine. So I was discussing about the question based on the class week 3 class. So as we have discussed earlier, the rearrangement reactions and carbocation stability. Today we are going to discuss some reactions based on carbene. So the question number 1 is here: among the following transformations, which will not generate carbene? So here we have 4 options. So we'll discuss one by one, and where is carbene is generated or not, we will see. So as you can see, the first option number, sorry, so here we have diazo compound first, right? And if it will go, what which type of fragments will get generated? You can see here this way, right? It will get generated, and when these two are the similar same fragments, so we will have here 2, right? So 2 radical fragments will generate over here because of and we all know that diazo compound leads to formation of carbene, but in which case, when it is on terminal position or diazo is attached to only one carbon. But here we have this diazo which is attached to both the carbon, so that's why it will form the radical one, not the carbene. So this option eliminate, right? Now talking about the option number B, we can see here we have Cl, LDA. LDA is a base, right? Bulky base. Why is bulky base? Because of its size, right? LDA is a very large size. That's why it is a bulky base. It will act as a base, so it will abstract the proton. So after the proton abstraction, what will happen? It will become, sorry, negative, right? So this is also not generating desired carbene one, carbene moiety, right? Then we move to the third one. What is the third one? CCl3CON, which we can also write in this form, ONA, right? It is a salt. Now here you can see that when we are heating this one, this will can eliminate CO2, but it will not generate carbene. Carbene is a species which have a pair of electrons. There are 2 types of carbene. One is singlet, one is triplet. So sorry, yeah, triplet. So in singlet carbene, we all know that this type of pair of electron are present. Now talking about the triplet carbene, so one electron in same spin present like this way. So in short, carbene have pair of electron, right? Pair of electron. But here when it will get knocked out, there is a carbene generation is not possible. So that's why this option is also eliminated. Now let's talk about the D, which is shown here, CH2 and 2. We can write this way. I told you that diazo forms carbene, but when it's attached to a single carbon, here you can see that we have a single carbon, right? So because of this one, this diazo, this bond breaking will takes place. Now all of you know that nitrogen is nucleophilic. It will take the electron with this, both the electron will go with this one. So here we will have CH2, but because of bond breaking we will have here 2 electron pair. This is called a carbene. For carbene you should have 2 electrons, and it is electron deficient. Don't confuse between anion and carbene. I will discuss this also. So in anion what happens? Suppose we have here carbon anion, right? Whatever it is. Now in this case, what happened? Here we also have example carbon anion. we here when it was a 4 bond like this one 4 bonds, each bond is formed by 2 electrons sharing, right? So when the proton abstraction or electrophilic reaction is taking place on this species, what happened, the group which is taken by base or electronegative atom is without taking electron, so that electron is remain here only because of the electron pull. Because carbon is more electronegative than the hydrogen one, it will pull the electron to itself. That's why after going this one, 3 bonds will remain as it is, right? 3 bond remains as it is, but this 2 electrons which was used for this covalent bond will remain as like this, because a hydrogen atom is sorry hydrogen atom is removed, but electrons are there. So with 2 electrons we can also write negative charge here, right? This is the anion one. And when we are talking about the cation like this one, what happens, the living species take the electron with them and leave this one as a, if we will think about this carbocation, leave this like this. So this is electron deficient. Carbocations are electron deficient, right? Because pair of electron went with the electronegative atom. Now talking about the carbene, in this case also here 2 bonds are breaking. In carbocation carbon anion generation, only 1 bond breaks, right? In carbene formation, 2 bond breaks in which were involved. So 2 electron were taken by this diazo one. So now carbon valency have 4, carbon have 4 valency. So instead of this 4 valency, 2 is hydrogen, and those 2 are not covered. So those 2 are these 2 electrons, right? So that's why this pair of electron, you can sometime you will think like we can write this negative charge also, and negative charge means electron rich, but this is not the case. Here it is electron deficient because 2 bond breaking is taking place. So correct answer in this option is option number D. Okay. Now let's move to the next question. The total spin of the singlet carbene is. So as we have discussed, what is singlet carbene? This way, right? What is triplet carbene? This way. So in short, in singlet carbene, both the electrons are of, are present in a same orbital in opposite spin. Because all of you know the basic rule, in a same orbital the same spin is not possible, right? We have basic chemistry knowledge which is already, I guess all of you know that, so I'm just explaining this way. And whenever they are present in 2 different orbital, that time they can be in like this way, right? Same spin. But in the same orbital they cannot be in the same spin. So in singlet carbene, both the electron present in a same orbital in a opposite spin. While talking about the triplet one, we know that both the electron will occupy the different orbital, so the different spin can be possible. It is also possible this way, like opposite spin. One more possibility is there, this way, right? There are different permutation combinations for triplet carbene, but for singlet one, because both the electrons are present in a single orbital, same orbital, so it will always be in opposite spin. Now let's talk about the spin calculation. How you are calculating the spin? So spin is equal to, we have to add all the spin, right? And one electron have plus half spin if it is on uh, above side this way, and we are calculating minus half when it is down, correct? Now let's talk about the singlet one. One is up, one is down, so we will write here plus half, then minus half. Plus half minus half will get cancelled and it will become 0. So spin for singlet carbene is 0. Understood? If you have any question or doubt, you can ask me now. Now let's talk about the triplet one also, because here one electron, here one electron is there. Now we will have here spin. This is for singlet. This is triplet. Okay, triplet spin plus half, right? Both in above side. So it will become 1. So the spin for triplet carbene is 1 and spin for singlet carbene is 0. So the correct answer is option number A. All of you clear here? Any question, any doubt is there? Fine. Now I hope all of you are clear. Now we will move to the next question. Here, among the following carbenes, the most nucleophilic carbene is. So what's the criteria for nucleophilic carbene? Anybody? So we'll discuss what is nucleophilic carbene. So basic thing is that for a nucleophilic carbene, it should have both the electron withdrawing group next to the carbon of carbon. Okay. So the divalent species should be get electron density from the nearest carbon. Now we will write this one in a open form, then it will be more clear this way. Here we have phenyl rings. Correct? Okay. Now all of you can see that these phenyl rings are the ring which can pull nucleophilic behavior here, which can pull the electron density, because this is not in resonance with this one. Correct? And this will they have aromatic ring. They are aromatic rings. So aromatic rings are pulling the electron density and making these sorry. Yeah. So we have aromatic ring here, and because there is no substitution present on this aromatic ring, they are electron rich, right? Because pi bond delocalization is there. So because of this one, both the phenyl group are electron rich group. That's why this carbene will become nucleophilic. Nucleophilic means uh, more electron density is present, right? So let's talk about the option B, where we have methyl carbene, CH3 carbene. So when we'll talk about this one, this is not the carbene also, because we have this and this. What is this? We have discussed right now only. This is nothing but this charge, right? So this is an ion, not a carbene. So this option is already eliminated. It's not the correct one. Now let's talk about the option C. Option C have this way. Okay, this carbene, right? But here also, if we'll consider this also, here we have two chloro group which pull the electron density, and this is also not carbene because H is also written, maybe by a mistake. It should be Cl2 carbene, not CHCl2. So okay, if we will not consider this H also, so this is nothing but the electron withdrawing group are there. So both the chlorine atom have a electron because both the chlorides are electronegative atom, they will pull the electron density towards them, right? So kaise hoga ye? This one should be like, suppose we have bond here, so both the electrons should be near to the chlorine atom, because electron pull is more by this chlorine atom. So because of this electron shift towards the chlorine side, the nucleophilicity of this carbene will get decreased, because there are this carbon is not electron say surrounded is not here because of pull of electron. Withdrawing group always pull the electron, so making this carbon electrophilic. Sorry, electrophilic. So this is electrophilic carbon, not electron nucleophilic. So that's why this option is also eliminated. Now let's talk about the option D. Option D we have OMe, fluoro and carbon. Right? Now you can see that here this carbon is attached to two different groups. One is methoxy and one is fluoro. Right? So we have discussed that fluoro, bromo all are a electron withdrawing group. Electron because of electronegativity they will pull the electron density towards themselves, right? Now talking about the OMe group, this is this having a lone pair, which is electron donating group, electron rich group, right? So because of electron donation nature of this one and electron uh, withdrawing nature of this one, both the group are present on carbene. So that's why this carbene is known as ambiphilic, ambiphilic carbene. Why? Because both the groups are present, which making this a neutral. This carbene is become neutral because of both the group present on the carbene, electron withdrawing and electron donating. That's why we will call this amphiphilic. Ambiphilic. Now this option is also eliminated. So option A only the correct option, because this electron phenyl group, both the phenyl group are stabilizing the nucleophilicity of this carbene. So that's why the correct answer for this one is option number A. Understood? I hope all of you are clear here. If you have any question, you can ask me. Then we will move to the next question. Okay. Okay, next one is here. So write down the major product in the following reaction. What is the major product? You have to check the reagent given on the arrow. We can see here what's the reagent here, right? Diethyl zinc and diadomethane. So this reagent is used in a very famous name reaction. Can anybody guess this one? It's a very famous name reaction. Simon Smith. Sorry. Smith. Cyclopropanation also we can call it. Cyclopropanation reaction. Now with the name, I think all of you know which will be the product. So we have to make the cyclopropane simple, right? One carbon addition. So if we'll see the all the four options, only cyclopropane are present in these two, right? So among them, which one will be the correct answer? We have to find. So option A and option D is already eliminated, right? So we'll discuss here mechanism, how the reaction is going. So first of all, we will see here we have diethyl zinc and iodomethane. So what happened in this case? First it will form the intermediate which will further participate in the reaction. So we have to make that intermediate and then we'll see the reaction. Zinc, sorry, ethyl, right? And we have here CH2 iodo. Yeah. So better I will write my opening here this way. Okay, this will attack this way and it will form the intermediate which will look like zinc. Iodo, and one side the same ethyl group will remain, right? After this formation, what will happen next? Next, cyclopropionation will take place. How? The transition state I will draw here after this formation. Now we have our alkene. So I will write this side. We have this way, here, this one, and now on arrow we have our olefin. So in this olefin, because Simon-Smith reaction is a cyclopropionation reaction, so all of you know that cyclopropionation will takes place, right? But we have two double bonds. On double bond, Simon-Smith reaction takes place. We have two double bonds, so one double bond will undergoing the reaction. Now let's talk about which one. So for Simon-Smith reaction, the double bond should be electron rich, right? Now here we have two double bonds. Which one is electron rich? Here you can see that we have H, right? Now here we have H. Talking about when comparing both the double bonds, you can see here only hydrogen atoms are there and this is mono substituted. Only one carbon atom is attached to this double bond. Now talking about the second double bond, here we have carbon atom here and here also this one, and one hydrogen is here. So now let's talk about this substitution. This is electron donating substitution, because lone pair of electron is here. They can pull the pair of electron here, right? And making this double bond electron rich. So this is the electron rich double bond, right? So because of this one, this double bond will undergo a cyclopropionation and it will give a product. So now we have discussed which double bond will undergo in reaction, participate in the reaction. Now let's talk about the mechanism. Okay, so we have seen that with this diadomethane with the diethyl zinc will form the complex, right? After formation of this complex, what will be the next? I will write here. Okay. CH2. It is dotted line actually. Oh, sorry. This way. Okay. And the other group will remain as it is. After formation of this intermediate, bond breaking, bond making formation will take place simultaneously, and we will get here Sorry, this is solid bond. This one will be the product. Okay, elimination. So this is the correct answer. So whenever the Simon-Smith reaction will takes place, you have to find out the electron-rich double bond. So electron-rich double bond, that means the electron density around that environment, atmosphere, should be high. So we have chose this double bond because here electron donating group is there, oxygen lone pair are available here, which is making this double bond more electron rich. Also, this is a tri-substituted double bond. So because of that also, and there is no withdrawing group attached to this double bond, that's why the electron density increased on this double bond. Okay, so Simon-Smith reaction is nothing but the cyclopropanation. So we have initially what we have done, we have found out where the cyclopropanation is taking place. So two options were eliminated earlier. Now we have checked the electron density, and we found that this double bond is more electron rich. That's why the option number C is the correct answer. Okay, understood? Okay.